Hello friends, myself Dr. Gaurav Bansod. So I would be giving you some basic knowledge about the DSP, which is digital signal processors. So let me introduce myself. I am PhD in the domain of embedded security and I am teaching this subject digital signal processor to the undergraduate students affiliated to the Pune University. I am teaching at the Pune Institute of Computer Technology, the subject advanced processor. So in the advanced processor, the unit number 5 and unit number 6 deals with the DSP related contents. It is having a DSP related contents. So I am trying to prepare the e-content for the unit number 5 and unit number 6 of the advanced processor. So before actually deal with the syllabus, I thought of introducing you guys a basic prerequisite to enter into the unit number 5, which basically deals with the TMS 320C6X748, the DSP processor. So this slide, this PPT will cover the basic concepts that is prerequisite to understand the DSPs. So the DSP processors or digital signal processors are the microprocessors specifically designed to handle DSP task. Now when I say a DSP task, all signal processing elements, which includes the operation like convolution, DFT, fast Fourier transforms, all kind of filterings can be done with the help of the DSP operation. And as you know that all these operations are very much complex. And in the last 40 years, the computers are extremely capable in doing data manipulation and also the mathematical calculation. And all microprocessor can perform both these tasks, data manipulation as well as mathematical calculation, but it is very difficult to design the microprocessor which is optimized for manipulation as well as for the mathematical calculation. So there always exists the trade-off between this. So when I say data manipulation, I mean to say a processing, moving data from one point to another. When I say mathematical calculation, I mean to say operation happens in the ALU like addition, subtraction, multiplication and so on. So one of the biggest bottlenecks in executing DSP algorithm is transferring information to and from memory, because dealing with the memory is a very complex operation. The more you interact with the memory, the more latency will be there in your system. That's why ARM introduces a concept called as RISC architecture or load and store architecture, where only load and store are the only two instructions which deals with the memory. Rest instructions processes everything in the registers only. So the lesser we go into the memory section, there will be less latency and higher throughput. So in DSPs also, whenever we process the data, there will be samples from the input signals and also there will be the coefficients. There will be the program instructions which will be executed by the CPU, and there will be huge to and fro mechanism moving from a program memory to the data memory to the program memory and to the CPU. So then it comes with what kind of architecture that our DSP, digital signal processors, are having. Then it depends how efficiently my instruction gets executed in those DSP environment based on what kind of memory architectures my DSP, digital signal processor, inherit. So this comes to our next slide, which tells you what are the different architectures that exist in the DSP, which are von Neumann, Harvard, and super Harvard architecture. So as you know that in von Neumann architecture, there is a single address and data bus which accesses the memory. While in Harvard architecture, there are exclusively address and data bus for the program memory and address and data bus for the data memory. So there will be separate mechanism to handle the program memory and to handle the data memory in Harvard architecture. While in super Harvard architecture, it's a high performance DSP, we can say, which is designed by analog devices. And SHARC, which is also called as super Harvard architecture, SHARC, is used in variety of signal processing applications ranging from, you can say, a single CPU to the 1000 CPU radar processing computers. So, and it gives you good performance over other these two architectures, von Neumann and Harvard architecture. So what is the difference between Harvard and super Harvard? As you can see from the diagram, it introduces the two elements, the two new elements, which are instruction cache and IO controller. Now what is the role of this instruction cache and what is the role of this IO controller? As you know that in super Harvard architecture, there will be multiple address buses and multiple data buses which are there for the program memory and for the data memory. So there might be a conflict for fetching a data because there are multiple address buses. So this instruction cache in short addresses that conflicts. We'll come one by one on the point. And what is the IO controller? What IO controller basically does is it offloads, it executes IO transfers in parallel with the CPU execution. So it brings lot of parallelism when we are having an IO controller. We are having a separate controller which deals with the input-output data through DMA, a direct memory access. So there will be ADCs, DACs from where the data is coming in, and we are having a DMA and IO controller which take care of the data which is coming from the external peripherals and fed back to the data memory. So this instruction cache and the IO controller are the two elements. When you introduce these two elements in the Harvard architecture, it becomes super Harvard architecture. So this super Harvard architecture is the term coined by the analog devices, and it is also called as SHARC, as I mentioned in the previous slides. Super Harvard's supers S, Harvard H, and architectures ARC. So the idea is to build upon the Harvard architecture by adding features to improve the throughput. And how the throughput will be introduced, or how the throughput will be increased? By introducing a two parameters called as instruction cache in the IO controllers. So let's talk about the instruction cache a bit. As you know that in the basic Harvard design, where we are having multiple address and data bus for the program memory and the data memory, my data memory bus is bit busier than the program memory bus, because there are n number of data which flows into the system as compared to the program memory, where it executes only the program instruction. It will execute only one program instruction, but that program instruction can consisting of multiple data which comes from the data memory. The whole idea is to reduce the load of the data memory by doing a balancing act, by relocating the part of a data to the program memory, so that the program memory also gets the equal load as compared to the data memory. And the third point is, you always know that in DSP, most of the instructions will be executed in a repeated manner. So let's take the example of a convolution. In convolution, we need to delay the signal, shift the signals, then add, then multiply. We need to do it repeatedly. In DFT, we need to do repeatedly the operations. So we will be spending most of the time in for loops. So there will be repeated operations like A multiplied by B plus C. So I required some kind of arrangement where these repeated operations are stored in a spatial memory where they execute in a more faster way. So the superhero architecture takes advantage of this situation by including an instruction cache into the CPU. So what this instruction cache memory? It's a small memory that contains 32 of the most recent program instruction. So it stores 32 of the program instruction that takes off the load of the data memory. And it helps the CPU, the core, to execute that 32 of the most instruction in an efficient way. So the program instruction can be pulled from this instruction cache instead of moving from program memory to data memory. Instead of having a conflict, I can use this instruction cache in an efficient way. And definitely when we talk about the I/O controller, what I mean to say is there will be n number of peripherals which are connected to my DSPs like ADC and DACs, and they will be throwing the data. If I don't have I/O controller, the CPU takes the load of handling all this data from the peripheral device. Now I'm having an I/O controller which takes the responsibility of taking these data, feeding it to the data memory with the CPU's intervention, with the CPU's authorization. So that's why we use DMA always. The data comes from all these peripherals through DMA. Everyone knows the concept about direct memory. It is one of the most efficient access that any CPU or processor or a controller has if you have a DMA unit. So in DMA, I don't have to every time, the external peripherals who require a resource don't have to go every time to the CPU saying that we required memory, please allot the memory. Every time it has to not request the CPU. At the first time, the external memory asks the CPU, I required, for example, 40 KB of memory, and CPU allots that 40 KB of memory in a one go instead of allotting 1 KB, 1 KB, 1 KB, 1 KB. And all the external peripherals takes the 40 KB of, so there will not be any interruption by the CPU till the external device finishes that 40 KB of memory or interfacing or sharing. Yeah. So if the external device requires more than 40 KB of memory, definitely it has to again go to the CPU and ask the permission, I require extra 40 KB of memory. The DMA is very efficient. So that's how the I/O controller plays a very important role. Okay, so this is the typical DSP architecture where you are having a data memory, program memory. There will be a exclusive address and data bus to the program memory, exclusive address and data bus to the data memory. You are having a data registers, multipliers, ALUs, shifters. You are having a program sequencer which is CPU. You are having an instruction cache which is having the 32 most recent instruction which takes the load from the data memory and try to execute this small part of memory in an efficient way. And by the way, cache is a very small memory. Everyone knows the storage memories, like we are having a secondary memory like hard disk, primary memory like RAM, and these are the memory like cache. So it is very important for a programmer to understand and store the important or the frequently used resources into the cache. So for example, you take the secondary memory as it's a colony of 10,000 houses, primary memory as colony of 1,000 houses, and the cache like memory is a colony of 10 houses. So definitely accessing a cache will be way faster than accessing the RAM or accessing the hard disk. So we should be very careful in putting the resource into the cache. If particular resource, if OS knows it's in cache and the user is by mistake did not allot that space in the cache, then we are increasing the turn. Then OS looks into the cache, it did not find the resource, that is called cache miss. Then it sees into the RAM, it did not find the resource, then it goes into the hard disk. So we are increasing more number of turns. So if we not design the cache carefully, then there will be more latency. So we should be very careful in designing the cache. Alright, so this is how the typical DSP architecture look like, which is Shark, which has a DMA IO controller, which is operating through a DMA and the instruction cache. Okay, why we need DSP? Because we know that most of the signals are analog, we need to convert into digital, we need to compute it, we need to process them, we need to first sample, then quantized, we need to use a reconstruction filters, we need to have a lot of ADCs and DACs. And most important reason we require DSPs to perform complex operations like multiplication, addition. These are very complex operations. For example, A is equal to B multiplied by C plus D. Now this, if we execute in a processor like Motorola 68,000, then it requires around 10 clock cycles for addition and 74 clock cycles for multiplication. Why? My DSP processor can execute this in a single clock cycle. We are having a unit in DSP called as MAC, a hardware unit, multiply, add and accumulate. So it's a hardware unit, just like we are having a hardware unit in LPC214 called as barrel shifter, inline barrel shifter, who take care of shift and rotate operation. So this multiply, add and accumulate unit can perform all this thing in a single clock cycle. So that's why DSP is a bit important. And there are various advantages associated with the DSP. There will be disadvantage in terms of cost. There will be disadvantage in terms of speed when we are having a large signal to get executed. There will be n number of applications areas the DSP is currently dealing with, starting with the image processing to the military applications, to the telecommunication, to the biomedicals. We are having n number of things where DSPs are used. And these are basically the DSP operations we talked about, where we are doing convolution, correlation, digital filterings, discrete transformation, modulation. So I hope you guys understood the basics about what for the DSPs are used, what is Harvard 1 Newman and super Harvard architectures, what's the typically DSP architecture look like. Okay, so it will be a bit easy for us after this conversation to enter into exactly what's the unit number 5 and unit number 6 is about that DSP TMS processor. Okay, so in the next video we'll actually deal with the TMS 320 C6X748. Thanks a lot.